Hello. So this is lecture 2 about summarizing distributions. And we're going to start off with this question. So when do you use the mean versus the median? Okay. And this question is best answered by, of course, an example. But first, let's talk about what the mean is. The mean is just an average of the numbers. You've probably done many averages. And the median, of course, is the middle number when you arrange all the numbers in your data set from in an ascending order, right? So when would you use a mean? Okay, let's get an example. So say you have a mean. Okay, say your data is like this: 1, 2, 3, 4, 5, and then 100. Okay, so you have 6 number of points, right? And just by looking at this data, you can kind of tell that this value 100 is kind of off. It doesn't really belong here, but it's here, right? So the mean in this case would be 5 plus 4, 1, 15, 105 divided by 6. So it would be 19.1, right? So that's your mean. And your median would be, what would your median be? So this is the lower half, upper half, 3. So your median would be the average of 3 and 4, which would just be 3.5. Okay. So to understand why we should use the median in this case, let's think about what this data represents the time in seconds it took someone to run 50 meters. Okay, so you can see that this person takes 1 minute, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. So you would assume that the person runs between 1 and 5 seconds, 50 meters, right? But then all of a sudden you have this outlier of 100 seconds, right? And what do you observe? You observe that just by adding this outlier, the mean has significantly gone up, right? The mean has significantly gone up, and it's giving you a wrong estimate of what exactly is the most probable time in seconds for this runner, right? But if we look at the median, well, the median isn't affected by this 100. It doesn't care. It doesn't matter if it's here, because what it is doing is it's only taking, when you arrange the values in an ascending order, you're really just focused on what it's by definition what occurs in the middle, right? And in this case, it happens to judge the time it takes a person to run 50 meters much accurately. So that gives it an important observation, which is also tip number 1. Median is resistant to outliers. Okay, so that's the first tip. Okay, so now you know when to use the mean and the median. Okay, and by the way, this symbol mu means population mean, and this symbol x bar means sample mean. So population mean, of course, is taking a mean of the entire data, and the sample mean would be, say I only took a mean of 1, 2, and 3, or some random 3-digit, some random 3 entries from the data, right? And that's the sample. Okay. Okay. So say I added the mean is 19.1, right? Okay. Now say I added a 1 to each of these points, so the 1 would become a 2. So my new data is 2, 3, 4, 5, 6, and then 101, right? Now try to think about what happens as I do this. How's the mean going to be affected? Okay. Well, if we're adding, so the way to think about this is how many times are we adding that constant k? Well, we have 6 elements, and we're adding it 6 times then, right? So this is essentially the same as, if I cross this out and go back to the original one, this is essentially the same as adding a 6 at the end, right? Because I've added the constant 1 each time, right? And in fact, we can just generalize this to k, the constant. 6 doesn't matter in this case. And then, okay, say it's 6, okay. And then, when you take the mean, you're of course going to divide by 6. But see what happens here. This computation can be split up into 1 plus 2 plus 3 dot 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 till 100 divided by 6 plus 6 divided by 6, which is 1, right? So you can see that the mean will also, the mean equals to the current mean plus the constant k. In this case it would be 1, as seen over here, right? So that's what happens to the mean as you add a constant. The mean, the resulting mean, also gets added with a constant. Okay, let's think about what happens if you're instead multiplying a number now. Okay, so say you're multiplying. Okay, say you have 1, 2, 3, 4, 5. Was it 100? 3. Yes. Okay. Now say you multiply all of these by 2. So you would have 2, 4, 6, 8, 10, and 200. But there's no need to do this, because what are we doing essentially? We are simply multiplying by a factor of 2, right? And this is basic factoring. So instead of multiplying everything by 2, we can just factor out a 2, and then we can write 1 plus 2 dot 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 100, and again we will divide by 6. Okay, so what does this tell you about the mean? It's the resulting mean, right? You know that the resulting mean, therefore, is also going to be multiplied by this constant k, because every single term is being multiplied by it. So the resulting mean must also be multiplied by that constant, correct? Yeah, okay, cool. So there's what happens as you add and multiply constants to a multiplication. Now, important tip number 2, I suppose, is it must be a constant. Oops. You cannot add, I cannot be like, okay, I'll add 1 to one value, then I'll add 2 to another value, and then I'll add 3. That doesn't work. You've got to add one number. That's how the algebra works out to be, as we just saw. Okay. Okay, so let's move on to the measures of variability. So I'll take this data. I've made some sample data. Put it here. Okay, so we already learned about range in the last lecture, so I won't touch on it. The range is max minus min, and we know that. Okay. Let's see. And of course, so the important thing to know about range is it's also not resistance. So like the mean, it's influenced heavily. And in fact, this is why I create this sample data set. You can see that, again, the value falls between 2 and 7, really. But because of these two extreme outliers, the range is now 250. 200 minus 50, right? Which is not correct, really, because it doesn't really describe where the data, like how far apart the data is spread, right? Because the outliers are skewing it in, I mean, not in both directions, but your tails now on the distribution are way longer than and they're stretched out more than they need to be, because the data might, for example, it's closer together if these two outliers were not present, right? So you would not use the range again when you have outliers. So what's a better way? Well, the better way, of course, is to use something called IQR, interquartile range. So if I erase this definition of range now, let's talk about what IQR means. IQR, as you can guess, it's you can't guess, but the IQR is resistant to outliers, okay? And to be resistant, now you can probably guess that it makes use of the median. If the range makes use of the mean, then the IQR makes use of the median to be resistant from outliers. So how does it do this? Okay, well, it divides the data into 4 parts. You have, first of all, an upper and lower half. So this is the upper half, that's the lower half. This is, of course, the median, right? And then this upper half and lower half are even more divided. They're divided further into Q1 and Q3, as we call them, Q1 and Q3. Q3 is the middle 75% of the data, and Q1 is the middle 25% of the data. So this value here would be Q1, that value there would be Q3, this would be the mean, that would be the minimum, and that would be the maximum, right? Now what the IQR does is, this is very important, it averages the middle 50% of the data, right? So what is the middle 50%? Well, that's just Q3 minus Q1, correct? And in this case, 7 minus 3 is 5, which is a much better estimate than the range, because remember, the range said it was 250, right? So the IQR is much more resistant to outliers because it makes use of the median. And a numerical rule, as stated in the textbook, is first of all, you take this value, 1.5 IQR, and if you add this to Q3 and you find out that any point in your data is above this value, so this plus Q3, then you know it's an outlier. And similarly, if you take this value, if you take Q1 minus this value, then you know for a fact that that value is, and so any value less than this will also be an outlier, okay? So there's using Q1 and Q3. Let's see. And once again, it's resistant. Okay, and let's look at the final measure of variability, which is called the variance and the standard deviation. So what is the variance really measuring? Well, the variance is it's really measuring how far, on average, are my points from the mean. So that phrase is important. It's measuring how far, yes, okay. So how far, I will write this down. How far are all points So this word on average is important. So it'll make a little more sense if I give the formula. So this formula for standard deviation is oops. Okay. So this is the formula for variance, not standard deviation. This is the formula for variance. And as you can tell, it looks kind of like a mean, right? Except it's measuring how far your values are on average from the mean, just like this does. This is actually tip number 3. Okay, and so a couple of things to note here is the variance. So this is called, when you see this symbol sigmoid, this is population. And this, if you see this as a little s, that's sample. Now, in the sample variance is actually given by this formula. Now, like if you were like me and you're wondering, well, where does this n minus 1 come from? Here it's just n, right? Then I advise you to look at something called Bessel's correction. I don't know if there's 2 s's or 1. I think it's 2. Bessel's correction. Okay, so you might not be able to understand it yet because the notation for the proof is a little bit different. But a quick googling on Wikipedia should familiarize you with the notation. And then you'll be able to see that this provides something called an unbiased estimate. So I encourage you to Google this, Bessel's correction, and yeah, read about it. Okay. So that is the variance, and then you have this thing called a standard deviation, which is just the square root of the variance. Okay, so you square root this, and then you get your variance, which is simply that. Okay, and so this for population, and for sample, of course, you just have an s. Okay, so that's your variance and standard deviation. Okay, now let's see what happens as we add to the variance. So just like we did the mean, we added stuff to it and then we saw how the mean changes. Well, with the variance, if you add stuff to it, it won't change. And my best intuitive explanation for this is by drawing a distribution. Say I draw a distribution like this, right? Say my data is like this, okay? Say this point over here is 1, that point over there is, I don't know, 3, okay? Say my variance is some number, I don't know, I will say 1.5, okay? Now when I'm adding, okay, when I'm adding a constant to each point in my data set, well, what am I really doing? I'm taking this distribution here, I just want to select this part. Okay, so I'm taking this distribution here, and I'm really just shifting it around a bit. Right? That's all I'm doing. If you should pause the video and try to make sense of what is really happening here. Is when I add, say I add 1 to this, say I add 1 to all the values in the data, I'm just shifting this distribution. I'm taking the 1, and what used to be 1 is now a 2. But all I've done is shift the distribution. Every other thing about the distribution is the same, except I just shifted it. So that is why the variance doesn't change, right? But, okay. But it does change with multiplication and division, and that isn't in chapter 2. So we'll get to it where it is, okay? I think it's in chapter 3 or 4, I don't know. But we'll get to it then. But for now, just remember that variance. This is tip number 4. Variance doesn't change. With addition or subtraction. Okay. Now moving on to what is the most critical part of this lecture, which is z-scores, and z-scores, and we already did changing units, so just z-scores, and also the bell-shaped distribution and the empirical rule. Okay, so what is a z-score, first of all? And I really encourage you to think about what this means. I'll give you the definition, my own definition. How far am I from the mean? That is a definition of a z-score. How far are you from the mean? More specifically, the question, how far am I? Well, we just answered it here. We can formalize how far you are with this expression, right? So now so what they did was, this is the standard deviation. I mean, it's not the standard deviation, but it's saying how many, we can reword it, how many standard deviations am I from the mean? Okay. More formally, if you care, it's written as x minus the mean divided by the standard deviation. And if I rearrange, you should be able to rearrange it too. So standard deviation multiplied by the z-score plus the mean equals 2x. Okay. Once again, I must emphasize this: the z-score is really simply telling you how many standard deviations are you away from the mean. That's all it is telling you. Okay. Okay, let's see, what else is there? Okay, cool. So, wait a minute. Okay, right. So that's the z-score, and the biggest part with the z-score is this distribution. I've taken this picture from Google, and what I want you to look at this distribution. So this is a bell-shaped symmetrical distribution, and usually we refer to it under. Yes, Okay, yeah. So this is a bell-shaped symmetrical distribution, and in these distributions only does something called the empirical rule applies, which basically tells you that within one standard deviations on either side, you will encompass 68% of the data. Okay, so between the z-scores of -1 and +1, 68% of your data points will be there, given that the distribution is bell-shaped and symmetrical. Okay, and within 3 standard deviations on either side, you will have almost all of the data, 99.7%. Okay, so that's what you need to remember, the empirical rule, and also that it only applies to bell-shaped and symmetrical ones. Another useful thing that I read in the book was that the standard deviation is between 1/4 and 1/6 of range. And they didn't go into detail about why this is the case or why it's true, and I haven't been able to prove it as such, but it's a handy little trick. So this is tip 5, because anytime you're given a problem and you're given range or something like that, you can use this theory, and then you can find out if your standard deviation is it a reasonable standard deviation. You can use it to solve problems. Okay. Finally, there's only one more thing left, which is yes. So remember, so we're going to talk about shape of the skewed distribution now, and so say I have a skewed distribution to the left, okay, and if I have a skewed distribution to the left and my mean, okay, now I want you to think about the median first. The median, of course, is not that resistant to outliers, so assuming that this part of it wasn't even here, that gives you an estimate of where the median will be, and it'll be somewhere over here. Okay, but in reality this part is here and the mean is affected by it, so the mean will be slightly over here because the outlier will pull the mean, towards it. Okay, so when the distribution is skewed left like this one, your mean is smaller than your median. That is tip number 6. If left skew. Okay, and you can I hope you can reason out what is going to be for right skew. I'm not going to say that. You can reason out yourself. What else is there? Okay, and there's only one more thing left, which is this so the variance. Remember I said what we talked about what happens when you add stuff to it? Well, later in the book it does talk about what happens when you multiply stuff to it, and as you might have guessed, multiplying the standard deviation by something multiplies it. So say I have a constant b, right, and I multiply that constant for all data points in my distribution, then the standard deviation will be multiplied by this. Notice tip number 7. Notice that this isn't the variance, it's the standard deviation. Because the variance is the squared of the standard deviation, this actually becomes b squared if you have your variance. So if you're using your variance, make sure you use b squared, and if you're using standard deviation, it's b. Okay, that is all there is to convert units. So how they test you on converting units is basically they'll give you a problem. They'll be like, oh, okay, so we have a bunch of data in Celsius, and then what's the mean in Fahrenheit? Or say I got my mean in Celsius, and then I wanted it to convert to Fahrenheit. What's my new mean? What's my new standard deviation? And if you know if you know the tip number 7, you'll be able to do that easily. Okay, let's see what else is there. Yeah, so last lecture we also talked about how the median divides the area of the histogram into 50%. Now you can think about the mean as sort of being a balance point. So think about it this way: if you had the histogram on your hand, which point would you pick so that it balances itself out? And that is the mean. And usually you don't need to think about this. The most they make you think about it is just these distributions, skewed left and skewed right. That's the most usually you have to think about it. Okay, and there's, what else is there? Box plots. So you should already know what a box plot is because you should have read the textbook. But a box plot is basically a way to graph your 5-number summary. So over here we talked about it. So the mean, so the box plot basically graphs your median, your median, Q1, Q3, maximum, and Q1, minimum, Q1, maximum, Q3, and median. So the box plot graphs all of that, and the biggest plus point with the box plot is indicates outliers. So that's why if you want to find outliers, you should use a box plot. Okay. Now that we are done both of these chapters, you should be able to answer. So, and another major point is this idea of describing distributions. And after this chapter, you should be able to describe distributions as well. And let me see. So I made this short note guide. It's just a paragraph. It gives you all the pointers about everything you need to say. So it's just a picture really. I'll see if I can embed it in here. But okay, but that photo will be in the description of the video, so you can just look at it, and that tells you everything you need to describe any distribution that we've dealt with in chapter 1 and 2. Okay, thank you. Read the textbook, do the questions, and we'll see you in chapter 3.